Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Yusuf and B09211045, and I will start our presentation by explaining about PMK 4253 project-based learning based on the title Reducing the Drag Coefficient based on an Ahmad Moody using ANSYS Fluence. Thanks to our lecturers, which is technology sama fakulti Pinang. So I will start by explaining the current group member, which is started by ALIFF HAIQAL, Muhammad Yusoff is me, NORHAIZAD, Muhammad KHAIRUDDIN, Muhammad MUSTAQIM, and also the last being KHIRUSNAPRAKASH. Okay, so for the chapter 1, I will start with introduction, which stated here, the Ahmad Moody is a simplified reconstruction of a passenger vehicle that has been focused of considerably computational fluid dynamics, which is CFD research due to its complex flow characteristic and significant contribution to automobile aerodynamic performance. Several methods have been developed to minimize drag coefficient of the Ahmad Moody, with the ultimate goal of increasing fuel efficiency and vehicle stability. The goal of the project will be to use an ANSYS fluent powerful safety software to evaluate the flow around the Ahmad body and investigate alternative design change to reduce its drag coefficient. And for the next part is problem statement. So I will explain more that the automotive industry aims to enhance vehicle efficiency performance by optimizing aerodynamics, particularly reducing the drag coefficient, which is a high drag, increased fuel consumption and emission. And traditional internal testing methods are costly, time-consuming. Therefore, cost-effective approach like computational fluid dynamics CFD using software such as ANSYS Fluent are necessary for analyzing and minimizing drag in the vehicle design. And the Ahmad body is a simplified car model, which is widely used in aerodynamic studies due to its simple geometry and effective experimental data. Some research show that various techniques can effectively reduce drag. It demonstrates significant drag reduction through a vehicle arrangement and active aerodynamic control. Repeatedly, it can be found that modifying the rear slant of angle and a voltage generator can minimize flow separation and reduce drag. Despite the proven effectiveness of this method, a systematic approach to applying and optimizing them on Ahmad body using CFD is needed, which is this project aims to use ANSYS Fluent to implement and refine drag reduction modification on the Ahmad body itself, enhancing the understanding of aerodynamic principle and developing practical solutions for reducing the drag coefficient that will be leading to a more efficient vehicle design. So this problem statement lays for the groundwork for investigating the aerodynamic optimization of the Ahmad body using advanced safety tools to achieve significant drag reduction. So that's all from me. Thank you. I will continue about the research routine. So this now one is to analyze baseline aerodynamic characteristics of the Ahmad body using CFD. Objective number 2, implement and evaluate drag reduction techniques. And the last objective is to optimize aerodynamic design for maximum drag reduction. And for the scope for this research is mainly focused on the aerodynamic optimization of the Ahmad body, which is a simplified car model to reduce the drag coefficient using computational fluid dynamic simulation in ANSYS Fluent. So for the first one, we will scope the project based on the baseline aerodynamic, application of drag reduction technique, optimization of aerodynamic design, comparison evaluation, practical application that recommended. Okay. So that's all from me. Thank you.
So, as for now, I will explain on the literature review. For the first one is introduction of Ahmad body and drag coefficient. The task intention is to apply ANSYS Fluent to put in force and optimize several enhancements to decrease the drag coefficient of the Ahmad frame. Student will get a deeper comprehension of CFD methodologies and aerodynamics principles via iterative simulations. Their capability to lay out cars could be stepped forward by way of this practical know-how to be able to also advantage the bigger discipline of car aerodynamics. Through the incorporation of sensible design adjustment with CFD simulations, the mission complies with cutting-edge studies tips and technological traits inside the industry. So now we move to the next one, which is computational fluid dynamics, CFD, in aerodynamics. CFD has revolutionized aerodynamics by enabling detailed simulation of fluid flow over complex geometries like the HAMID body. This computational approach leverages numerical methods to solve the Navier-Stokes equations, offering cost-effective and time-efficient alternative to traditional experimental testing. CFD facilitates in-depth analysis of drag reduction strategies through shape optimization and surface modification, contributing significantly to advancement in automotive, aerospace, and sports engineering. Despite challenges in validation and model accuracy, CFD remains pivotal for optimizing aerodynamics performance and enhancing design efficiency. Next, technique for drag reduction. Numerous methods for lowering vehicle model drag coefficients have been found through research with an emphasis on both passive and active aerodynamics control measure. Modifying the vehicle's shape geometrically using vortex generators, fairings, or changing the rear slant angle are examples of passive approaches. With these changes, the flow around the car should be more efficient, which should reduce flow separation of vortex formation to significant cause of drag. According to Munir 2022 investigation of the impact of various vehicle configuration on aerodynamic resistance show that careful vehicle alignment and positioning can greatly minimize drag. For instance, staggered vehicle arrangement can reduce drag forces by minimizing the wake size. Like this, Zhang 2023 investigated a truck model application of steady blowing and active aerodynamic control method. They were able to change the flow field surrounding the vehicle, lowering pressure drag and increasing overall aerodynamic efficiency by delivering control jets of air at specific point.
Hello, Sir Hafizi. I'm KHIRUSNAPRAKASH. I'm from BMKA 1/2 and the metric number was B0921102161. Okay, today I'm here to talk about the modification and optimization. The HAMID body has been modified to enhance its aerodynamic performance through shape adjustment and the addition of aerodynamic features. Research by Ali and Brisrohr that showed that adjusting the rear slant angle, especially to around 25° effectively balance vehicle stability with reduced drag by minimizing flow separation behind the vehicle. Saleh and Ali focused on vortex generators, which are a small device generating control vortex to delay flow separation and energize the boundary layer. Placed strategically on the HAMID body, these vortex generators were found through computational simulation to effectively reduce drag. This highlights the critical role of comprehensive CFD model in optimizing aerodynamic modification. Additionally, spoilers and rear diffusers were studied for their impact on drag reduction and vehicle stability, showing how spoilers adjust flow separation to lessen drag forces, while rear diffusers manage airflow beneath the vehicle and also reducing pressure drag. As we see practical and application result using analysis fluent to reduce the drag coefficient of the HAMID body has proven effectively in practical applications. Researchers have utilized detailed simulation to implement shape optimization, surface adjustment, and aerodynamic enhancements such as vortex generators. This effort consistently show significant reduction in drag and also improving vehicle performance and fuel efficiency. Analysis fluent facilitates iterative testing and design improvements, allowing engineers to achieve notable aerodynamic advancement without costly physical prototypes. This practical application highlights the impact of computational fluid dynamics in advancing aerodynamic research, benefit industries like automotive and aerospace. Okay, as a summary in chapter 2, the task intention is to apply NC Fluent to put in force and optimize a number of enhancements as a way to decrease the drag coefficient of the HAMID frame. Students will get a deeper comprehension of CFD methodologies and aerodynamic principles via interactive simulations. Their capability to lay out cars could be stepped forward by way of this practical know-how to be able to also advantage the bigger discipline of car aerodynamics. Through the incorporation of sensible design adjustment with CFD simulations, the mission compiles with cutting-edge studies, tips and also technologically straits inside the industry. That's all from me. Thank you.
Okay, now I will be present for the chapter 3, which is model setup. So for the introduction, CFD simulation setup, by using ANSYS Fluent, set up a CFD simulation of the flow around the HAMID body based on their assigned target element count. The simulation setup will include importing the HAMID body geometry, defining appreciate boundary condition and selecting the desired turbulence model. So here this is flow chart. As you can see, is starting by start, capital B5, meshing quality validation, boundary conditions, CFD calculation, CFD processing, grid sensitivity analysis, result and end. So here the dimension of HAMID body, which is benchmark design, modification 1, modification 2 and wind tunnel. So for the setup automation to this setting, as you can see here the figure, the flow of how to do a process of setup automation to this setting. So next is a setup tetra mesh 3D setting. As you can see here, see the flow of the procedure to do the setup tetra mesh 3D. So finally we go after after the meshing. For the tetra mesh 3D, we will export the file to the ANSYS Fluent. So now we will set up the ANSYS, which is firstly we start the workbench and then go to the Fluent and import the mesh after we done in the setup 3D tetra mesh. So we will use the ANSYS Fluent to calculate the all dimension that have been shown for the HAMID body design, which including the wind tunnel. So here after we put the value of in the ANSYS Fluent, we will use the parameter for the calculation, and then the calculation will be pop up the graph and the diagram of turbulence, and then it will be calculation complete.
Assalamualaikum and a very good day. My name Muhammad NORHAIZAD bin Rukiman, matrix number B0921110060. Next, I will present about chapter 4, which is result. Firstly, introduction. The project focused on aerodynamic optimization of the HAMID body, a simplified vehicle model using CFD in ANSYS Fluent to reduce the drag coefficient. The research involved analyzing baseline aerodynamic characteristics, implementing drag reduction technique, and optimizing the design for maximum drag reduction. This is a calculation for velocity. The velocity can be got by RE times by dynamic viscosity over density times characteristic length, and the velocity we got is 13.98 meter per second. Firstly, the result is drag coefficient, which is for benchmark is 0.213, modification 1 0.348, and modification 2 0.25. Next result is pressure coefficient, which is CD. For benchmark, maximum pressure coefficient is 1.07, modification 1 1.07, and modification 2 1.05. Next, pressure. For pressure result, first for benchmark 1.01 exponent 5, and then for modification 1 1.25 exponent 1, and lastly modification 2 1.25 exponent 2. For third result is velocity. Firstly, for benchmark 2.15 exponent 1, for modification 1 2.18 exponent 1, and modification 2 2.32 exponent 1. And then for summary of the result is the modification led to significant reductions in drag compared to the benchmark design. Firstly, modification 2 was the most effective, showing the lowest drag coefficient and highest aerodynamic. Number 2, modification 1 also reduced drag but was less effective than modification 2. The result highlighted the importance of geometric modifications in reducing drag, with plots providing visual evidence of improved aerodynamic performance. The project demonstrates the potential of using CFD tools for optimizing vehicle design to achieve better fuel efficiency and performance. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Alif HAIQAL bin Abdul Hamid and my matrix number is B090115. So today I am going to present about chapter 5, which is conclusion. So for the conclusion, in this study, the aerodynamic performance of the HAMID body was evaluated and optimized using computational fluid dynamic analysis in ANSYS Fluent. 2 modifications were made to the standard HAMID body design, altering the rear slant angle and adding vortex generators for modification 1, and introducing a chamfer pillar design with a 40-degree angle, which is modification 2. Both modifications demonstrate significant reduction in the drag coefficient compared to the bench design. Specifically, modification 2 with its innovative chamfer pillar showed the greatest promise in reducing aerodynamic drags, achieving the lowest drag coefficient and indicating superior aerodynamic efficiency. The pressure distribution were more uniform in the modified design, suggesting reduced flow, separation, and vortex formation. Contour plots of velocity and pressure further illustrate smoother airflow and lower pressure regions around the modified HAMID bodies, especially in modification 2.
So overall, the systematic application and optimization of these modifications using CFD tools provided a clear understanding of the aerodynamic improvements achievable through such design changes, highlighting the potential for significant drag reduction and enhanced vehicle aerodynamics. So that's all from us. Thank you.